Hello. So today we're going to continue what we started last time, which was spaces of continuous time signals with the infinity norm. Okay, and what we did last time was we saw, in fact we showed, that if the time domain is compact, then a few things hold, all of them rather related to one another. Oops. Okay, so first is these three generally different spaces of signals are the same. And moreover, one space, and therefore all of them, are complete in the infinity norm. Okay, so that gives us a nice class of Banach spaces, namely the continuous signals on a compact interval. Okay, today what we're going to do is we're going to relax one thing first, which is the compactness of the time domain, and then we're going to begin the process of relaxing the use of the infinity norm. Okay. Okay, good. As I said, the case we have to think about is the case where T is compact, okay? And then what we'll see when T is compact is that, we always have inclusions like this, okay? And what we're going to see when T is compact is that you have strict inclusions. You don't have equality ever, sorry, when T is not compact, okay? So we claim a couple of things. If T is not compact, then the space of compactly supported signals in the infinity norm is not complete. Okay, so remember the story here that we started a few lectures ago is that this is kind of the class of signals that we felt like every continuous time signal space should contain. Okay, so this is kind of the building block of all of our continuous time signal spaces. All right, and so that space is never complete in the infinity norm, okay, when the time domain is not compact. And so that means either not closed and or not bounded. Okay. And the other thing is that this string of equalities is just inclusions. Okay, and you'll remember my convention that if I want to allow the possibility of equality with an inclusion like this, I do it like that. Okay, so this means strict inclusion. All right. Okay, I think maybe it's illustrative to do the easy thing here first, because it kind of makes us think a little bit about what the non-compactness of the time domain, what the impact of that is. Okay. So there's kind of two cases to consider. All right. Two representative cases to consider. So again, not compact can mean can fail by either virtue of unboundedness or not closedness. Okay, so let's first consider where the case where T is bounded but not closed. Actually, let's consider the other case first. So it's closed but not bounded. And it's really enough to consider an example of one such thing. And let's take the closed interval from 0 to infinity. Okay, so we're going to consider inclusions between these spaces of signals. All right, and I'm really just going to draw examples of something in here which is not in here, and then something in here which is not in here, and that'll be enough to show that these inclusions are strict. Okay, okay, so we're looking at functions defined on the positive half line. So let's take the constant function 1, or any non-zero constant that you like. Okay, so this is so this function is clearly bounded. Okay, but it also clearly does not have compact support. Its support is all of the positive half line, which is not compact, and so the support is not compact. And so this gives us that C0 CPT is contained in C0 bounded. Okay, and as another example to show the other inclusion. Okay, so again, we're talking about functions on the half line. Okay, again, tons of examples. For example, let's just take a function with linear growth, say f of t equals t. Okay, so this will certainly be continuous, but it's not bounded. So this shows that C0 bounded is contained in, but not equal to C0. Okay. All right, so that's how boundedness affects these containments. Let's now look at the case where T is bounded but not closed. And again, it really suffices to just consider an example. Let's consider the half open interval from 0 to 1. Okay. And so again, all I need to do is kind of give you an example of something which illustrates the two strict containments. So first, let's find something. So we're open here and closed here. Okay, so I want to find something which is bounded but does not have compact support. Okay, so again, the constant function works here. function 1. Okay, so this shows that C0 CPT is contained strictly in C0 VDD. Okay, so let's actually verify here that this function f does not have compact support. Okay, so the support of f. Okay, so the definition of the support of f is that you take the closure of the set of points T, which f of t is non-zero, and then you intersect that with, well, the time domain, which in this case is 0, 1. Okay, so f is non-zero everywhere on here, and so the set inside the braces is the open at 0, closed at 1 interval. Then I take the closure of that. Okay, so I get 0, 1. Okay, but the crucial thing is that I need to intersect it with that again. And that's not compact. Okay, so the support of f is not compact in that case. All right, so the other kind of example is one which is continuous but not bounded. So I have an interval which is open there. And here you can take a function like just 1 over t. Okay, so that blows up at the open interval 0. It's still continuous, right? There's no problems, at 0, because 0 is not actually in the domain of your signal. So so no problem with it being continuous, but it's also not bounded. Okay. Okay, good. So that kind of illustrates why compactness is required to get equalities like this, and that without compactness, all you're going to get are these inclusions. Okay, good. Now let's look at the first question here about the completeness in a non-compact time domain of the space of continuous signals with compact support in the infinity norm. Okay. Okay, so again, I'm not going to go through proofs here, but what do I need to do? What I need to do is I need to, in the case of a non-compact time domain, find a Cauchy sequence in here which doesn't converge in here. Okay, so I need to find a sequence of continuous signals with compact support that doesn't converge to a continuous signal with compact support. Okay. All right. And so let's first, so we're going to kind of do the same thing as we did up here, and we're going to consider the two possible cases of T closed but not bounded. Okay. Okay, so I need to think a bit maybe for a second to see how to find a Cauchy sequence of signals which in the infinity norm, okay, which doesn't converge. Now, the strategy that I'm going to use here is going to build off the intuition that I developed when we looked at discrete time signals. All right, so in discrete time signals, we started with in the infinity norm. When we looked at things on an unbounded interval, we started with C finite, so finitely supported signals, and then we saw that the completion was little c0. Okay, and we saw this was the completion in the infinity norm. All right, And we reasoned there. I'm not going to repeat the reasoning again here, but we reasoned why this was a good choice for the completion, or I should say a good guess for the completion. And then I, sort of illustrated to you without any details at all, how you would go about proving that this is the completion of this in the infinity norm. Okay, so we're going to use a similar strategy here. We're first going to try to guess at why this space isn't complete by understanding, sort of this process by which we were led to the completion. Okay. And the fact is, a similar sort of phenomenon happens here. So when you think about a function with compact support, what's it going to look like? It's sort of going to look something like that, right? So it's going to, have a compact support, right? So you need to have a sequence of things like this. So it should somehow converge in the infinity norm, and that means uniformly. But what we need to do is we need to ensure that the limit that we get violates this the compact support condition or the continuity condition, but it turns out that the thing you're going to violate is the compact support condition. Okay, so really what I should do, therefore, is think about a sequence which converges to a continuous function, which a Cauchy sequence in the infinity norm, which is converging to a continuous function that doesn't have compact support. Okay, that's the idea. All right, and sort of motivated by the construction that we did in the discrete time case, seems reasonable that what you should do is you should choose a function which goes to 0 at infinity. Okay, that's going to kind of be the limit of your sequence. Okay, and so you could, for example, take f to be 1 over 1 plus t squared. Okay, and that's going to have a graph which looks something like this. Okay, and so the point is that it doesn't exactly look like it. The point is that it converges to 0 at infinity. All right. All right, so that's going to kind of be my starting point. Okay, so and again, this is just a guess. All right, now what we did in the discrete time case was we, looking at it in retrospect, what we did in the discrete time case was first we took a signal that converged to 0 at infinity, and when we did this, we were talking about sequences, and then what we did was we just chopped off the tails of the sequence further and further out. Okay, and so you could think about maybe doing the same thing here. That if this is 1, say, and 2, 3, and 4, and so on, you could think about chopping these functions off, right? So f1 would be this. Okay, and f2. So I don't normally use colors, but here's a good place to use colors. Okay, so f2 would be chopped off there. Right, and then similarly, f3. Actually, let me choose something a little more visible. There. Okay, so right, and so f3 would be this function. So okay, and so on. Okay, well, those aren't actually good choices. Well, they're terrible choices, but the reason is easy to repair. The problem with f1, f2, and f3 is that they're not continuous, right? So in the discrete time case, we didn't have this problem, but these f1 is discontinuous there, f2 is discontinuous there, and f3 is discontinuous there. But you can kludge that up easily enough by for f1, just sort of sending the thing down to 0. It doesn't matter really how you do that. Okay, so here's just one way to do it. And then f2, send it down to 0. and then F3, you send it down to 0. Okay, so now what I have is I have a sequence of continuous functions. There's F1, F2, and F3. Okay, they're compactly supported. Okay, so their supports are, the support of F1 is the closed interval from 0 to 2. The support of F2 is the closed interval from 0 to 3, and F3 is 0 to 4. Okay, so there's our guessing done. Okay, so now that you've made the guess, what do you have to do? You have to show that the sequence of functions F1, F2, F3, and so on that I've constructed in this way, and all you need here is just some function f that goes to 0. So I've given a specific one, but it doesn't really matter. You just take any function f that decays to 0 at infinity. And then build this other sequence F1, F2, F3 of continuous, compactly supported signals in exactly the way that I've illustrated. And then when you do that, what you can show is Cauchy, but doesn't converge. Okay, and I want to make it super clear what I'm talking about, so it doesn't converge in here. All right. Okay, so you have some work to do to prove that, right? But the strategy for doing the proof is very, very similar to what we did in the discrete time case when we were looking at things like this. Okay. All right. So remember what you do there is you prove that if it converges, then it's going to converge to this function f. Okay, so at every time t, it's going to converge pointwise to this function f, which you use to build the sequence f1, f2, f3, and so on. And then you notice that the function f that it must converge to is not compactly supported, so therefore it doesn't converge. Right? Okay, so that's what happens in the closed but not bounded case. Now, for the bounded but not closed case, okay, we're going to use a similar kind of reasoning, okay, without giving proofs. The proofs, once you have the right thing to prove at hand, the proofs are not hard. And again, they follow very closely the strategy that we used in the discrete time case. All right, so, but the trick in all of these cases is kind of getting the idea. And for functions defined on the interval open at 0, closed at 1, okay, it's clearly this open interval at 1, which is going to cause me problems. And here we saw that we were going to go after the violating the compactly supported condition, and so we're going to do the same thing here. And we were given some guidance here about what can happen. Okay. And so at 0 here, you can blow up but still be continuous. You can be bounded, okay, but not have compact support, okay. And so in fact, this seems like it might be a decent guess here for the function that you're going to converge to. All right. So in other words, you start out here with a guess of a limit function which doesn't satisfy the conditions that define your space, in this case continuous with compact support. So this is such a function. So the function 1 on the interval open at 0, closed at 1 is continuous, but it doesn't have compact support. Okay, so is that a good choice? Well, in fact, it turns out that it's not. And the reason that it's not is that you can build a sequence of continuous functions that converges to this thing, but it will not converge uniformly. Okay. All right. So therefore, it won't be a Cauchy sequence. All right. And so it can't be this function. Okay, so you have to think again. All right, now you get a clue from what's happening here. So what happens here is that we chose this thing to decay to 0 at infinity. So it seems maybe reasonable that the right thing to do here is to choose a function that is continuous but decays to 0 at 1. Okay, so remember 1 is not included in the domain, so it's not equal to 1 to 0 at 0, but it's decays to 0 at 0. Right, so a function like this. Okay, and I'm going to use the same kind of strategy here to build a sequence of F1, F2, F3. Okay, and you're going to truncate. Okay, but it's a little different here. It doesn't work. You don't really have a nice analogy anymore with the discrete time case. But you know, at least the analogy isn't so strong. But you can still think about doing it, right? So, sorry. All right. So we're going to again do the chopping business. All right. So we're going to chop this thing by at points which are getting ever and ever closer to 0. Okay, and so we get a function f1 that we obtain in this way. So there's f1. We get a function f2 by truncating. Okay, and then a function f3 like so. Okay, but again, these have the problem that they're not continuous, right? So F3 is discontinuous there, F2 there, F1 there. But you use rather a similar strategy to what you did here. That is, you just kind of force them to be continuous by shooting them down to 0. And the only thing you have to do is you have to make sure, you can't do it, for example, by sending it to 0 at 0. You have to send it to 0 at some strictly positive value. Okay, so F3 might do something like that. F2 might do something like that. F1 might do something like that. Okay, so F2, F3. Okay. All right, but the strategy is broadly the same. You choose a candidate function, and so again, in this case, you may choose ft equals t, for example, but lots of functions, anything that decays to 0 at 0. Okay. And then you choose a candidate function, which is kind of going to be your limit function, which doesn't actually satisfy the conditions of your space, namely in this case that it doesn't have compact support. Okay, and then you find a sequence that seems to want to converge to it. In this case, it's the sequence F1, F2, F3 build like so. Okay, and then again, once you've guessed the right answer, the rest of it is kind of straightforward. Show that Fj is a non-convergent Cauchy sequence. And you really have to say what space it is that you're talking about here, because we're going to have a proliferation of different spaces with different norms running around, so you should be careful. Okay. And so the analysis here, again, can be modeled by what we did in the discrete time case, which is that you show that if this sequence, F1, F2, F3, built in this way does converge, then at any t in the domain from open 0, closed 1, that the sequence has to converge at every t to that value. Okay. And then you observe that this function is not a function of compact support. Okay, so the support of this function is calculated exactly the same way as this one. So the support is the support of f 0, 1. Okay. All right, and so because the function that you're converging to pointwise doesn't have the properties of my space, namely it doesn't have compact support, this gives me non-convergence. Okay, so that's more or less why this space is never complete. Okay, because the behavior at endpoints of your interval, which are not closed, or the behavior at infinity, causes the existence of these non-convergent Cauchy sequences. Okay. Okay, excellent. Now, what we should do, now that we've answered these, we've done these things, is we should give the completion. Now, the way I built these two non-convergent Cauchy sequences very clearly is meant to suggest what the completion is, right? So in the case of the closed interval from 0 to infinity, I'm clearly suggesting that the completion should be the space of all continuous functions that decay to 0 in exactly the same way as the completion in the discrete time case was the space little c0 of signals that decay to 0 at infinity. Either plus or minus infinity. It's a little bit different here. You're still going to get this decaying to 0 property, but this isn't, in some sense, this isn't really at infinity. But in some sense, it is at infinity. Because this point 0 is as much in the interval, open interval 0, 1, as the point at infinity is up here. Okay, which is to say, it's not in it. Okay, you can get closer and closer to it, but you can't actually get there. Okay, and so in both cases, I'm clearly suggesting that the completion here should be the functions that decay to 0 at infinity. Here it should be the functions that decay to 0 at 0. Okay, and you can imagine now all of the other possibilities of non-closed, non-compact intervals. If you're open at both endpoints, then it has to decay to 0 at both endpoints, and if it's closed but not bounded at minus infinity, then it has to go to 0 at minus infinity. All right. So one way to give the definition of the completion here would be to give all of those special cases. All right. Of the closed but not bounded intervals. But let me not do that. Let me instead conjure a definition which covers all the cases at once. Okay. All right. So okay. So this is a fact that I won't prove, but I think should be eminently believable, and is quite straightforward to prove once you know that this is the result that you're after. Okay, and it's this: the completion of C0, CPT. And this is for all time domains, okay, including the compact case. So let me emphasize that. Okay, so it's a space which we're going to call C00, and it will use the infinity norm. Okay, and so this is a new collection of signals. I'll tell you shortly what it is, but of course the 0 here means continuous, just like it did all the other times before, and the 0 here plays exactly the same role as the 0 here. Okay, so the 0 here meant to suggest that it goes to 0 at infinity. Okay, and this is sort of the adaptation of that, and so let me say exactly what that space is. All right, so it's continuous Fs with the following property. For any epsilon positive, there exists a compact interval, and I'll call it S in T, so that f of t is less than epsilon for t outside S. Okay, and so this definition, if you think about it for a second, covers both of the, so it covers the compact case, okay, and because in the compact case, you can take S to be T, and then, there's no condition to check here because the set is empty. Okay, so this just means that it's the set of all Fs in C0 which satisfy a condition which doesn't satisfy an empty condition because that set is empty. Okay, so it works in the compact case. Good. Now, in the unbounded case, all right, it's pretty clear how this definition functions. All right, you just take, your S is just going to be, you choose some interval which is large enough so that outside that interval, which means, from here off to infinity, because the function is sort of decaying to 0, the value of the function is small. Okay, so this definition captures the decaying to 0 at plus or minus infinity part. Okay, but it also works here. Okay, so I also want to see how this definition or this condition gives me convergence to 0 at 0 in this case. All right, and so the compact intervals that I'm going to choose here are going to look like this. Okay, and so the idea is that outside a compact interval that looks like this, the value of the function is less than epsilon. Okay, and by choosing epsilon smaller, if I make epsilon smaller, then I just have to make the compact interval bigger, getting closer to 0 here, to make sure that this condition is satisfied. Okay, so this is one sort of slick way. And if you look back at how I defined the discrete time signal space, little c0, this is exactly analogous to how I did it there. And there, instead of a compact interval, I had a finite subset S contained in T. Okay, so compact intervals in the continuous time case are rather like finite subsets in the discrete time case. All right. Okay. So that covers all of what we can say about continuous continuous signals on continuous time domains in the infinity norm. Okay, so this gives a complete characterization of C0 CPT TF infinity norm, okay, for continuous time domains. Okay, and I feel like I should say this because the number of the questions that we're asking here are quite limited. Namely, we're interested in asking, is the space complete? And if it's not, what's its completion? Okay, and that's its completion. Right now, let's look at one thing we did in the discrete time case was we looked at ordering these things, right? And so in this case of continuous time signals with the infinity norm, they're ordered in a nice way, okay? And they're ordered like this. So the smallest one is going to be C0 CPT. Okay, this is going to be contained in, okay, C0, C0, 0 is going to be the next smallest one. And then the next one is going to be C0 bounded. And then the biggest one is going to be, C0, okay, and all inclusions are strict if and only if T is not compact. Okay. And so, there's only one thing here that we haven't explored, and that's the insertion of this guy in this string of inclusions that we talked about before. Okay, so we stuck C00 in there. Okay, so let's see how that fits. So first I should find something in here, which is not in here. Well, I've kind of already done that in each of these cases, right? So in this case, I have this one. And in this case, I have this one. Okay. And then I should also find something in C0 bounded, which is not in here. Okay, but I also did that before. Okay, so this one in the bounded but not closed case, this F is in C0 bounded, but it's not in C00, and similarly in the closed but unbounded case. All right, so we've seen already that we've seen already this statement. Okay. So that's pretty much everything that we're going to say about continuous time signal spaces with the infinity norm. Okay. Now we're going to look at spaces of continuous time signals with the P norm, the P norms. Okay. All right. So let's maybe first see that the space is never complete. Okay, no matter, and this is true for any t, continuous time domain t, and any p. And here, I am just interested in this case because I've already covered infinity. All right, so let's illustrate that with an example. Okay, so the example that we're going to look at, again, so what I'm going to do is I'm going to draw the sequence. Okay. All right. So I'm going to talk about the closed time domain. So closed and bounded, compact time domain, interval from 0 to 1. Okay. So the signals that I'm going to talk about are going to be defined like so. Okay. So here's the value. One, and here's the value in the domain of half. Okay, and so from 0 to 1, these signals are going to be defined to just be, sorry, from half to 1, they're going to be defined with a constant value 1. Okay, and then what I'm going to do is I'm going to, now the sequence is going to vary from 0 to half. Okay. So the first function in the sequence is going to be that. The second function in the sequence is going to be that, and maybe let's say that point is a quarter. Doesn't really matter. Okay, so this is F2, and then F3. Okay, and this might be 3/8. Okay, so I choose to, and then this one would be 7/16, I guess. Okay. The only thing I really care about is that I have a sequence here that converges to a half from below. Okay. All right. So all of these guys are constant value 1 from a half to 1, and then as the sequence increases, they sort of start behaving like this. And so you can see my idea here is that I'm kind of hoping that this sequence will converge to the discontinuous signal, which is 0 from 0 to a half, and then 1 from a half to 1. Okay, so let's see why. Why this sequence doesn't converge in the p norm. Okay, and it doesn't matter which p we choose. Okay, now when we were first talking about sequences of non-convergent Cauchy sequences, we worked with spaces of signals. And so the thing that we were interested in understanding there were, Fj minus Fk for large J and K. Right. And so it's similar here. To understand what's going on with this sequence, we should look at Fj minus Fk. All right. And probably it's going to be Fk minus Fj. All right. So 1. So here's a half. Here's 1. Like so. Okay. So what I'm going to look at here is I'm going to think about what does the graph of Fj minus Fk look like. And again, it's probably Fk of t minus Fj. Okay. All right. Let's see which one it is that we want to look at when we see what goes on. Okay, so anyway, all of the FJs are equal to 1 between half and 1. So when you subtract them, that'll be 0. Okay, so the difference will certainly be 0 in there. Okay, All right, now what's going to happen is, so let's say that I'm looking at F2 and F3, just for concreteness, since I have them drawn, okay? Now, F2 and F3 are both 0 here. So I'm going to be 0 going along up until some point, okay? So let me draw that. So there's going to be some time, and the time is going to be exactly determined by, what J and K are. Okay, but then when I reach the value of the smallest index, okay, then that one is going to become non-zero. Okay, so actually, I guess if I'm taking K to be greater than J, then actually looking at this, okay, and here K is greater than J. Okay, so there's going to be some time, okay, where the FJ with the lower index between J and K is going to switch on. Okay, and so what's it going to do? Well, we know what it's going to do. It's going to go from the point here where it kicks in, and it's going to run up to that point. Okay, so let me not draw it in right now. Okay, all right, so then I'm going to go along. All right, and I'm going to be following the curve here until I reach the point where FK kicks in, and then I'm subtracting FK. All right, and then at the value half, they both agree. All right, and so I'm going to have. And so when you think about how that's going to work, I'm going to reach a point here. Okay, so this will let me call this point maybe TJ. Okay, so TJ is the point where FJ turns on, and then TK is going to be the point where FK turns on. So this will be TK. All right. So then what's my function going to do? What it's going to do is it's going to follow FJ here until it reaches the point where here where FK switches on, okay, and then it's going to gradually decrease to 0. Okay, so what I end up with, and this hat function, tent function, need not be symmetric, okay, because it all depends on where the point TK is relative to the point TJ, right? But it's going to basically look like that. All right. Okay, good. So now that we understand this, let's see if we can understand why this is a Cauchy sequence, number one, and why it doesn't converge. Okay. All right. So, oops. So we're going to first argue, and I won't go through all of the details here because it's going to be quite clear from the graph that I've drawn here. Okay. All right, so what do I need to do? I need to choose n large enough so that the p norm, okay, so need n large enough that the integral from 0 to 1 fj of t minus fk of t to the p dt 1 over p, right? That's the p norm, is less than epsilon. Okay, so you give me an epsilon, I need to find an n like that. Okay, so again, I'm not going to go through this carefully, but you see how this is going to work, right? You need to, if you choose your TJ, right? So TJ is kind of the when the first of the functions fj and fk switches on. If you choose TJ to be very large, okay, then you're going to be looking at both fj and fk are going to be functions that are bounded between 0 and 1. Okay, and if you choose J large enough, then the support of Fj minus Fk is going to be as small as you like. Okay, it's going to go from Tj to a half. Okay, so by choosing n large enough, we can ensure that 1/2 minus Tj, okay, so Tj again is making reference to this diagram, okay, is small enough that, and so maybe I should, maybe let me say Tn is small enough that the integral from 0 to 1 Fj of t minus Fk of t dt is less than or equal to the integral from 0 to 1 of Fj of t dt plus the integral from 0 to 1 Fk of t dt. Okay, that's just a triangle inequality. And so the point is that because, sorry, I apologize. I don't want to use the triangle inequality right at that point. I'm sorry. I need to leave it like I had it. And so the point is really this, that this integral is going to be the integral from 1/2 minus Tj to 1/2 Fk of t dt. Okay, and so then now I can use the fact that both Fj and Fk are bounded by 1. Okay, so this is going to be less than or equal to 2 times the integral from 1/2 minus, and sorry, this isn't Tj, this is the way I've done it, it's Tn. Okay, Tn to 1/2 dt is less than epsilon for okay, for n for sorry for j and k greater than or equal to n. Okay, so that's the idea. So again, you just choose n large enough so that if j is larger than n, tj is out there, and so we're talking about a function which is bounded by 1 and has a very thin support. Okay, that's what this is intended to convey. All right, so that's a sketch of why this sequence is a Cauchy sequence. Okay, now let's see why it's not convergent. Right, and the strategy here to prove this is very similar to the strategy we used in our discrete time non-convergent Cauchy sequences, and that is you let t be between 0 and 1/2 open. Okay, so we claim that if Fj converges to F, then F of t must equal 0. Okay. All right. Now, how do we prove that? And so, again, I'm just going to kind of draw pictures here about how this goes. Okay, so here's 1, 1/2, 0. Okay. All right, so I'm really interested here in what's going on between 0 and 1/2. Okay, and so what I'm saying is that I can take any t in there. Okay, and the interesting thing is kind of thinking about choosing t to be quite close to 1/2. All right, so let me choose t in there. Okay, so I'm saying it must be the case that if this sequence converges in the p norm, okay, to f, okay, and when I say converges, I mean it converges in the space that I'm talking about, okay, and the space that I'm talking about is that one, okay. So in particular, f is continuous, all right, okay. All right, so so I know that I have some f, which is continuous. It's the limit in the p norm of this sequence, and that at this point t, let's suppose that f is non-zero. Okay, so this is not true. Okay, so then, and if it's f is non-zero, again, as I've sort of done, we looked at a situation which is quite similar to this before, where if f is non-zero and it's continuous, we may as well take it to be positive. Okay, so f, let's say, has some value, f of t equals beta, which is greater than 0. All right. Now, by continuity, okay, so this is where we had an argument that's quite similar to what we did before. And so remember, this came up when we were talking about whether the p norms were a norm on C0. Okay, so if you want to see another situation where we used an argument like this, it was back then. Okay, so I know by continuity of f, okay, and that's an assumption because I'm assuming that I have convergence now in my space, which is the space of continuous functions and compact support. Okay, so I choose a little interval around t, so that if f is positive at t, it's also positive at every point in that interval. Okay. Now, what I do is I choose a capital N, large, so that Tj, or Tn, is out here. Okay, and so I know then that. Okay, so let me put some data on here. Okay, so let me suppose that this little interval has a width, which is 2r. Okay, so it's t plus or minus little r. Okay, so so here what we're doing is we're supposing that f of t is equal to some beta, which is positive. Okay, and in fact, I'm without loss of generality, I'm assuming that f is positive there. Okay, choose r so that f of let me call it s is greater than or equal to 1/2 f of t. Okay, so t is this fixed value of t that I chose. Okay, so that's true for s between t minus r and t plus r. Okay. Right, and so I need to make sure that there's some fussy business here, right? I need to make sure that r is small enough so that this thing is contained in 0, 1/2. Okay. Now, as long as I do that, then choosing n large enough that Tn is greater than T plus R, okay? So in my picture here, okay, this is going to be that point there is going to be Tn. And the point is that it's to the right of T plus R, okay? So it's in here, right? Now, as long as I do that, then I know that then if J is greater than or equal to N, okay, the integral from 0 to 1, f of t minus f j of t dt is going to be greater than or equal to, because I'm going to integrate over a smaller domain, the integral from, sorry, I can't use t there, s, okay, the integral from t minus r to t plus r, f of s minus f j of s ds. Okay, and now I've chosen j so that on t minus r to t plus r, fj is 0, right? Because j is larger than n and tn is there. Okay, so this is going to be greater than or equal to the integral from t minus r to t plus r, f of, and so f t is positive, so a half there. Okay, and so that's not a typo, right? So that t is constant with respect to what I'm integrating. And here I'm using this condition. Okay, so this is greater than or equal to r beta. Beta, which is positive. Okay, and that prevents convergence. Okay, so contradicts convergence. Okay, and so what you conclude for that is that that I can't do this, right? So f of t must in fact be 0. Okay, now this is true. For any t, okay, and so what we have concluded that is that if fj j so converges, the limit function should satisfy, okay, f of t equals 0 for t between 1 and a half, okay, and then now what about between a half and 1? Well, obviously, right? All of the terms in the sequence. If you take the function 1, between a half and 1, all of the functions in the sequence have the value 1, and so obviously they're going to converge to 1 from a half to 1. Okay, and so 1, where t is between 1/2 and 1. Okay, and there is no continuous function with that property. Okay, So that's how I show that the sequence doesn't converge. I show that if it does converge, then it has to converge to something that I can understand very well. And the resulting thing prohibits the convergence to a continuous signal. And I'm talking about the completeness of this space, the space of continuous signals with compact support. And so therefore that space is not complete. Okay. And so here, so I've done this in the case of the compact interval 0, 1, and you can easily construct such examples for any other kind of time domain. And again, the point is that this space with the P norm is not complete. Okay, for any T and for any P. Okay. All right. So then the question is, what is the completion? Okay. And the answer is it's complicated. Right, and we're going to take a significant diversion before we can come back, and our diversion will be long in time, but short compared to what you really need to say that all properly. But we'll take enough of a diversion so that we can get a sense of what the completion of this space is. Okay, but that'll all be starting next time.